The Lagrange or Taylor error bound, part 2. Recall that the error, or the remainder using the nth degree polynomial, is less than or equal to the max of the first left off derivative times x minus c to the n plus 1 over n plus 1 factorial. So given f of x equals cosine of 3x plus pi over 3, find an upper bound on f of 1 when using the second degree polynomial centered about x equals 0. So we're going to need to write the second degree polynomial, which means we're going to need to find values of the function at the center, 0, as well as values of the derivatives. So f of x is cosine of 3x plus pi over 3, which means f prime of x is going to equal the negative 3 sine 3x plus pi over 3, the extra 3 from the chain out. F double prime of x is negative 9 cosine 3x plus pi over 3. And I'd be done there for my polynomial, but I'm going to take one more derivative, which will give me 27 times the sine of 3x plus pi over 3. Now recall that it doesn't matter whether it's sine or cosine, that both of them are always between negative 1 and 1. Which means f prime would always be between negative 3 and 3, f double prime between negative 9 and 9, and f triple prime between negative 27 and 27. We'll use that in just a bit. But let's find some values. I know that f of 0 is a cosine of pi over 3, which is a half. F prime of 0 is negative 3 times the sine of pi over 3, which is negative 3 times root 3 over 2. F double prime of 0 is negative 9 times 1 half. So my second degree approximation is f of 0 plus, in this case, negative 3 root 3 over 2 times x minus 0 plus negative 9 over 2 times x minus 0 squared over 2 factorial. And I'll rewrite this one just to make it a little bit pretty for us. So f of 1, therefore, can be approximated by my second degree at 1, which is a half minus 3 root 3 over 2 minus 9/4. And I'll just call that a. Because my problem says find an upper bound on f of 1. Well, I know that f of 1 is my approximation plus an error. Really, it's no more than the approximation plus an error. So I need to find the error. That is, I need to find an upper bound on the error. So the error using the second degree polynomial approximation is less than or equal to the max of the first left off derivative times x minus 0 cubed over 3 factorial. But the max of f triple prime is going to be 27. Now why is it 27? Once again, because sine is between negative 1 and 1. So 27 sine is between negative 27 and 27. And then we're at 1, so I do 27 times 1 cubed over 3 factorial, which is 27 over 6, or 9 halves. which means that f of 1 is no more than my approximation plus 9/2. Let's take a look at another example. Let's find the maximum error using my third degree Taylor polynomial to approximate e to the point 2. It makes sense to use my center as 0 because 0 is close to point 2 and because I know the Taylor series or the Maclaurin series in this case because I'm centered at 0 for e to the x. But all I want to do is find the maximum error. I don't need to find the polynomial itself. And I know the following fact, that the nth derivative of e to the x is always e to the x. You might need more precision, but for me, if I'm approximating e to the x on the interval 0 to 1, I know that e to the x is always between 0 and 3. I could be more precise, but for me that's good enough. Which means that the remainder using the third degree Taylor approximation is no more than 3, the max of any derivative of e to the x, times my first left off power, so x to the fourth or x minus 0 to the fourth over 4 factorial. And then plugging in, because I'm doing x equals 0.2 to get my approximation, I have 3 times 0.2 to the fourth over 4 factorial. Which means that using my third degree Taylor polynomial approximation centered at 0 to approximate e to the 0.2 gives me an error that's no more than 0.0002. One final example, let's work it backwards. What is the fewest number of terms needed so that our approximation of e to the 0.5 is given by that? So these problems in general are going to be guess and check. I'm using the fact that e to the x is between 0 and 3 on the interval 0 to 1. So 3 is a nice number, it's good to use. And then I'm going to guess and check. What if I did, let's let n equal 3. Then my error is no more than 3 times 0.5, that's the x value I'm trying to approximate for the function. So I do 0.5 to the fourth over 4 factorial, which gives me 0.0078, which is not less than the error needed. So what if I try the fourth degree polynomial? Then my error is no more than 3 times 1/2 to the 5th power over 5 factorial, which is 0.00078. Still not good enough, but I'm getting pretty close. So what if I try the 5th degree polynomial? Then my error is no more than 3 times 0.5 to the 6th over 6 factorial, which is equal to 0.0000651, which is not quite there. Without doing any extra work, I know well, I guess I'll show it to you, that if I do my next one over 7 factorial, I will get a value that is less than 0.00001. Which means I am going to use the 6th degree polynomial to approximate e to the x at 0.5. So the approximation is about 0, but I'm trying to approximate e to the 0.5. Which means I'm going to use the first 7 terms. That is, I need to do the x to the 0 term all the way out to the x to the 6th term. And if you count those out, that gives us 7 terms.